in English will be more comprehensible to foreign visitors. Okay? So the topic of this course is equivariant cohomology. Okay? So equivariant cohomology is essentially the algebraic topology of a space with a group action. So in this first lecture, I would like to explain what it is, what we are trying to do, some of the results, and some of the applications. Okay. Okay. Now, the prerequisites for this course is 1 semester of manifolds and 1 year of algebraic topology. Okay? So I assume that you know what a manifold is and that you can work with differential forms. And you know what the fundamental group is, singular homology and cohomology. Okay, so I assume that you know all this. Yeah. If you don't know a few facts, you can always look it up in a reference book. So now, cohomology, well, with any kind of coefficients, it's a functor from topological spaces and continuous maps to rings. And ring homomorphisms. Okay, so that's what cohomology is. And it gives you invariance of topological spaces. Okay? Okay, now in this course, we're going to look not at just topological spaces, but topological spaces with a group action. Okay? So let me first define a group action. An action of a group G on a space X. Okay? So is a continuous map from G cross X to X. Okay? And the way we write it is that it takes Gx to G dot X, okay, such that the identity times X is X. And then if you have two group elements, G dot H dot X, that's the same as GH dot X. Okay, so for all GH in G. Okay, so that's a group action. And here's an example. If you take a sphere and you rotate it, okay, you can rotate it by any angle between 0 and 2 pi. So you rotate it about the z-axis. That's an action of the circle on the two sphere. Okay? So rotating a sphere about the z-axis is an action of S1 on S2. Okay? And so a space with a group action by G is called a G space. And then equivariant cohomology it's an analog of cohomology. So it's a functor from the category of G spaces and their morphisms to rings. Okay. So the first thing that I will do in this course is to construct such a functor. Okay? And there are many possibilities. Okay? And so we will see why, like, one particular construction is better than others. The others. Okay? Now, in algebraic topology, so we define this cohomology functor. Here, this is the singular cohomology functor. For a manifold, if you have a manifold, then you have the Ram's theorem, okay? Because the Ram's theorem says that singular cohomology, which is defined in terms of continuous cochains, can be calculated using differential forms. Okay? So the Ram's theorem says that for a manifold, for a C infinity manifold, M, there's an isomorphism between singular cohomology with real coefficients and the cohomology of the complex of C infinity forms. Okay? I write that as omega M. Okay? So where omega M is the complex of C infinity forms, differential forms of M. Okay? Now, it's usually much easier to work with differential forms than with singular cochains. Okay? So the Ram theorem is quite useful, as a computational tool. Now, in equivariant cohomology, there is an analog of the Ram theorem. Okay? So it is called the equivariant de Ram theorem. And the equivariant de Ram theorem says that we can calculate equivariant cohomology, which is defined topologically using differential forms. But there's a group action, so you need more than differential forms. You need equivariant differential forms. So now, so the equivariant de Ram theorem says that now we are in the C infinity category, so G will be a Lie group. Let G be a Lie group, and M a C infinity G manifold. And so it is possible to construct a differential complex, okay, out of, that would be denoted by omega GM, out of C infinity forms on M and the Lie algebra. G of G, okay, such that equivariant cohomology can be computed as the cohomology of this complex. Okay? So this complex is the equivariant analog of the de Rham complex of differential forms, and it was defined by Cartan. So it's called the Cartan complex. Omega Gm is called the Cartan complex. Okay. And there is a differential, okay, which is the analog of the exterior derivative, and it's called the Cartan differential. And you compute the cohomology, with respect to the Cartan differential. Okay. And then the elements of the Cartan complex are the equivariant differential forms. Okay. So equivariant differential forms, they're not the same as ordinary differential forms. They involve the Lie algebra also. So for example, for the circle, if the Lie group is a circle, then equivariant differential forms will be polynomials in a variable u whose coefficients are invariant differential forms under the group action. Okay? Maybe I'll write that down. So for example, if G is S1, then the Cartan complex, it consists of the sum of alpha I ui. Okay, so I goes from 0 to some n, such that alpha I are invariant differential forms on M. So differential forms on M that's invariant under the action of the circle. Okay? And this N, I mean, it could be anything. Okay. Now, equivariant homology is very useful because it can be used to calculate ordinary integrals on a manifold. Okay? So in general, it's really hard to calculate integrals on a manifold. But in equivariant cohomology, there is a theorem, a localization theorem, equivariant localization theorem, which is due to Attia and Bott and Nico Berlin and Michel Vernier, okay, in 1982. So this theorem is only for a torus action. Okay? So let G be a torus. So a torus is a product of finitely many circles. And M, a compact oriented G manifold with isolated fixed points.
Excuse me.
Yeah.
So, in your example there, the U, is it just a formal variable or what is it?
Oh, yeah. Yeah. Oops. You can think of U as a formal variable when you do calculations, but actually it is yeah. So this depends on the choice of an element in the Lie algebra. Now, so if you choose an element X in the Lie algebra of S1, so the Lie algebra S1 is really just R, right? U, so you think of the Lie algebra as a tangent space to the identity of S1. Now, U is the dual. U is the dual basis. So X. So if you choose a non-zero element, yeah, X has to be non-zero. If you choose a non-zero element in the Lie algebra of S1, then it's a basis, right? And so U is the dual basis for the cotangent space. Yeah. Yeah, that's what it is. However,
So usually the I is a wedge product. So
pardon?
usually the I is a I wedge product.
Oh, no, then you form the symmetric algebra, right? So it's just a polynomial in U. Yeah. 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 So you can, yeah, you think of it as a formal variable. So it's just a polynomial in U whose coefficients are invariant forms. But I think, yeah, we are going to use this interpretation, somewhere. Okay, that's where it came from. Good. Okay, so the equivariant localization theorem says if you have a torus acting on a compact-oriented manifold with isolated fixed points, then when you integrate an equivariant differential form, okay, so like if you integrate this, the integral of this, you just integrate the coefficients. Okay? Just leave that U alone. That's how. So the integral is going to be a polynomial in U. Okay? So if if omega is an equivariantly closed form, you see, an equivariant differential form, it's in the Cartan complex, and the Cartan complex has a differential. So you can talk about closed forms, equivariantly closed forms. Okay? It just means that the Cartan differential of omega is 0. Okay? So if you have an equivariantly closed form, then the integral of omega over m, okay? So in the case of a circle action, you just integrate each of the coefficients. Now, most of the time you'll get 0 because the dimension isn't right. Okay? But if the alpha I has the same dimension of the manifold, then you'll get a number times ui, right? So in general, you're going to get a polynomial in U. That's what this integral is. And this integral, according to the theorem, is a sum, a finite sum over the fixed points. Okay? And at each fixed point, you have a polynomial in U, okay? And I'm going to explain what it is later, but right now I'm just going to write down the formula. So the formula doesn't make too much sense to you, but what this is that you take omega and you restrict it to P. Yeah. Now, you see, omega is a polynomial in U with coefficients that are differential forms. When you restrict it to P, most of the terms will disappear because if the form has degree more than 1, then when you restrict it to a point, it will be 0. Right? However, this could be a 0 form. A 0 form is a function. So when you restrict it to P, it gives you a value. Okay? Yeah. So that's what this means. You restrict the omega to P, and then you divide by the equivariant Euler characteristic of the normal bundle of P. Okay? Well, nu P is the normal bundle of P. Well, actually, P is a single point, right? So the normal bundle is just the tangent space. Okay. But I want to treat it as a bundle so that I can define characteristic classes. Okay? And EG is the equivariant Euler class. Okay? So I'll have to tell you, what an equivariant Euler class is. Right? And then this is a great formula because an integral is usually difficult to compute, but a finite sum is much easier to compute. Okay? So of course, you have to be able to compute the equivariant Euler class. Now, this is actually a polynomial in U divided by another polynomial in U. So this is a rational expression in U. Okay? But the very amazing thing is that when you sum up these rational expressions over the fixed points, you end up with a polynomial. Okay? That these rational expressions somehow they cancel each other out in such a way that the sum is a polynomial. Okay? So this is going to be in yeah, no. Okay, now you expect this to be a polynomial, right? Yeah. Yeah, right. And so this side turns out to be a polynomial. With real coefficients. Okay? If you are using S1 as a group, now if it's not S1, if it's a torus, then it's going to be a polynomial in several variables instead of just U. Okay. Okay. Yeah. And now this theorem, okay, allows you to calculate the integral of an equivariantly closed form, but as a corollary, it actually gives you a method for calculating an integral of an ordinary differential form. Okay? And so that's another thing that I will explain in the course. Okay? So this theorem gives a method for calculating the integral of an ordinary differential form. Okay? Okay. So the two main theorems in the course are the equivariant Theorem theorem and the localization theorem. And that's what I will try to explain and prove in this course. You know, it's hard to say like who proved the equivariant Theorem theorem first. So Cartan proved it for one case, for the case of a free action of a compact Lie group. And then the rest is kind of like, you know, technical details. So I think it's not really attributed to anybody. But it's not really very well written down in the literature, you know. Yeah. And it took me, you know, many years to figure out, you know, how to present it in a way that's kind of understandable. So, so finally I put it in the appendix in the book because it's a little bit technical, yeah. And I want the book to be easy to read. So in the main body of the book, you know, everything is really easy. And I put the very hard stuff in the appendix so that people who are a little bit short of time can skip it, you know. But I think we will go through it in the course, okay? Okay, so basically that is the content of this course. Do you have any questions? Yeah. You know, if you have any questions, I welcome you, you know, to raise your hand because sometimes you think that, oh, maybe I will just go home and think about it, you know. But maybe it's because I didn't explain it very well. So you should ask me, you know. And your questions will help me to revise this book. So the reason I'm offering this course is that I would like to get some feedback, you know, about the book. I want to make it really easy to read. So, you know, if you encounter any difficulties, you should let me know, and I'll try to find some other way to explain it. Okay? Yeah.
So I want to ask that in your course topic you talk about the Fourier construct and will be proved in the class that the cohomology of classified space over the group will be like Taurus will be the polynomial of any variable. But will you be proved in the class?
Okay, so the question is, will I prove the localization theorem for a torus action?
Cohomology for the classified space, BG.
Oh, will I calculate the cohomology of the classifying spaces?
Yeah. Because there's a,
Yeah.
I think in the papers article about they mentioned it specifically.
Yeah.
They didn't prove it.
Yeah, yeah, I think I will prove it. I think it will come out as a corollary of the equivariant Theorem theorem. Yeah, because the cohomology of the classifying space of a group is the equivariant cohomology of a point.
Yeah.
Yeah, right. So, yeah. So it will be a very simple case of this, right? M will be a point. Yeah. Oh, another thing I want to say is that although the course is in English, you're welcome to ask questions in Mandarin. Okay? I do understand Mandarin. I may not know how to say equivariant cohomology in Mandarin, but I can understand Mandarin. Yeah. Okay. Okay. So I think the first thing that we want to look at is how to define equivariant cohomology. Okay? So what we want is a functor from G spaces to rings. Can you think of a functor from G spaces to rings? A very simple one, a trivial one. What is the most trivial functor you can think of? Ordinary cohomology. No, because I guess. Well, I mean, the functor has to respect morphisms too. Well, okay, I haven't defined morphisms for G spaces, but I think you can imagine what it should be, right? So let's first define a morphism of G spaces. So if X and Y are G spaces, then a morphism from X to Y, well, it should be, first of all, it has to be a continuous map. Okay? And then you have to respect the group action, so such that f of g dot x is g dot f of x for all g in g and x in x. Okay? So that's a morphism. And well, a map like this is also said to be G equivariant. Okay, a map with this property. Okay. So I think you cannot just take ordinary cohomology because it doesn't respect. Can you do that? Ordinary cohomology. Yeah, somehow you want to involve the group, right? Yeah. So, yeah. Well, I mean, there are many possibilities, So, for example, I think I can map everything to 0, right? I think that is a functor, a very good functor. Yeah. And that's also easy to calculate. Yeah. But it doesn't give you any information, so not very useful. Okay. So you kind of have to make a delicate trade-off between computability and information, So, yeah, so anyhow, it seems like a very natural thing to do is to take the quotient of x by g, and then take its ordinary cohomology. Okay. So, candidates. Oh, let me see. What time am I supposed to stop? 4:20. Okay, yeah. So candidates for equivariant cohomology. Now, the first candidate is you can take the ordinary cohomology of the quotient space, x by g. Okay, so x by g, it just means you take the space of orbits. It's the space of g orbits. Okay? So every element is an orbit. Okay? So let's look at an example. That z acts on R by translation. Okay? So n dot x, that means you translate x n units, x plus n. Okay. Now, so what are the orbits? No, what's the orbit space of this? Like, so 0 is the orbit will be, the orbit of 0 will be all the integers, right? You translate 0 by an integer, and then the orbit of a point here will be here, 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 or on the other side also. Right? So what's the orbit space? The orbit space is, yeah, the circle, because 0 is the same as 1. And then, like, every orbit has a representative in this interval. But 0 is the same as 1, so you have to identify 0 and 1. So the orbit space is this interval with 0 and 1 identified. So it's a circle. So here G is Z, M is R, and then X. I'm going to call it M because that's a manifold. M over G is S1. Okay? That's the orbit space. And so the cohomology of M mod G is the cohomology of S1. Okay? And you all know what the cohomology of S1 is, right? So it's R in degrees 0 and 1, and then 0 otherwise. Okay? So, very good. So if we call this the equivariant cohomology, we get something interesting, right? Something non-trivial. Okay? Now, let's look at another example. So, we will look at this example a lot. The action of S1 on S2 by rotating about the z-axis. Okay? So S1 acts on S2 by rotation. Okay? What is the orbit space in this case? Pardon? Huh? Yeah, the unit interval, right? Because the orbit of this point is just this horizontal circle. Now each point has this horizontal circle as the orbit, except the North Pole and the South Pole. You know? And so here the orbit space, here G is S1, M is S2, M mod G, the orbit space, is the interval, this interval. But the cohomology of the interval is trivial because the interval is contractible. So the cohomology of this is the cohomology of a point. Okay? And that's trivial. Well, you see, here you have a very interesting action. Okay? But the cohomology of the quotient space gives you nothing. It's the same as acting on a point. So, I mean, this suggests that this isn't such a good candidate, okay? Because if you have a good theory of equivariant cohomology, you should get some interesting answer for this example also, okay? So now, what is the difference between these two examples? They are both group actions, but there's one difference. Right. How are they different? Huh?
There are some fixed points.
Okay, yeah. This one doesn't have any fixed points. This has fixed points. Yeah. You know, but that's not why this cohomology of the quotient space isn't good. Okay, so yeah, it's true. You're right that this one has fixed points, that one doesn't have fixed points. That's one difference. But what's another difference between these two examples?
One is manifold and one is orbital.
Oh, yeah, so the...
So the action is not 3D.
Right, yeah, you see, this quotient is a nice manifold, right? This quotient, well, it's a manifold with boundary. It's not a manifold. You start with a manifold, you end up with a manifold with boundary. And so that's because this action is not free, and that action is free, okay? So in general, when you have a free action and you take the quotient is nice. But if you have a non-free action and you take the quotient, then it may not be nice. You know, it may become not a manifold, or it becomes, it has singularities, or it's really, you know, it's completely weird. Yeah.
Is that the definition of free quotient?
So yeah, let me tell you what a free action is. Okay, so an action is free if the stabilizer of every point is the identity. Okay, so let's just. I think I'll just make the definition and then we can stop. Okay, so if G acts on X, then the stabilizer of X, it's the group elements that fixes X. Okay, that's a stabilizer of X. And the action is free if the stabilizer of X is the identity for all X. So You see here, if you want to calculate the stabilizer of x, then you have to find n such that x plus n is x. So that's if and only if n is 0, that's the identity, right? So this action is free because the stabilizer of every point is the identity. Now, here, here you can see that the stabilizer of the North Pole, let's call that P and Q. Here, in this example, the stabilizer of the North Pole, what is it? It's a whole group because P is a fixed point. And the stabilizer of the South Pole is S1. So this action is not free. Okay? And this one is free. Yeah, that is the main difference. Okay? Okay, so I'm going to stop here and we come back after 10 minutes and then we'll see, like how to define equivariant cohomology. Okay? Somehow you have to turn a non-free action to a free action. Okay? Okay, so let's stop for a while.